Hello and welcome to Team 4's ECE 4534 final presentation. Team of Eskandarian, Julian Nguyen, Keith Tiemann, and Alex Williams. Together, we create a real-time strategy RTS game. So, what exactly is an RTS? Well, unlike traditional games such as chess, an RTS does not progress incrementally in turns. This is a key factor and one of the reasons why they are so popular, as it adds a new element to the game. Players don't have too much time to think about their strategy and have to react quickly to the fast-paced nature of the game. Another point is that an RTS is usually played on a map or battlefield where players control their units and structures in an attempt to destroy or capture their opponent's assets. In order to do so, resources are accumulated and spent to generate more units and structures. Popular examples of RTS games are Rise of Nations, StarCraft, and Age of Empires. Overall, a common objective in an RTS game is to gather resources, build your units, and defeat your enemy. Our goal with this project was to create a real-life RTS using rovers and a physical game board. Our rovers would be able to play the typical roles of a worker and a soldier, the soldier to attack the opposing team, and the worker to go out and seek resources. These resources would be physical locations on the map. Finally, we had the town center, which would be a focal point for each team, starting point for all the rovers, and essentially the brains of each team. Now that we've given you the overview of our project, we'd like to go into more detail about the major components. First, we have the worker rover. As per the project requirements, the rover starts at one of the 8 adjacent tiles to a town center, has a representation of its current state, and is able to detect the color of an object or tile in front of it. As stated before, the objective of the worker is to navigate the map to seek out and bring back resources to the town center. Next, we have the soldier rover. Its requirements are the same as those of the worker, but differs in its objectives. A soldier rover roams the map to find and attack enemy rovers and the opposing team's town center. Town centers are required to be marked as a physical location on the map and the starting point for all rovers. In addition, a Raspberry Pi plays a role in the town center's implementation as it keeps track of resource deposits and the location of the rovers. The grid, our representation for a game board, had the requirements of being 7 tiles by 7 tiles. In addition, each tile could only hold one game object at a time, obstacles be marked by magenta, resources be marked by green, and tiles containing no objects to be a blank white tile. Finally, it is important to note the 4 main threads implemented for our project, and we will be going into detail on each one. Starting us off will be Kia to discuss the SLAM thread.
So for a quick overview of what this means and entails, in robotic mapping and navigation, SLAM aims to tackle the problem of both constructing or updating a map of the game environment, and also keeping track of where an agent is within the map. For our game, this meant keeping track of what is on the map and where our rovers are located. To solve this problem, we had 3 things we needed to accomplish. The first was utilizing a pixie camera to identify the tile the rover is facing. The second was to leverage incoming data from our server, and the third was to actually create the map given all this information. A more detailed explanation of this task breaks it into 2 discrete functions, the collection of relevant data and the actual construction of the map. First, I'm going to focus on the data collection, which is done in 2 different ways. Through a pixie camera attached to the front of the rover, and through communication with the server. The primary focus of my discussion will be on how the pixie cam works in conjunction with our project. This camera works by being taught a series of objects of different hues. In our implementation, an orange piece of construction paper is seen as a resource, and a magenta piece is seen as an obstacle. We were able to teach the pixie objects by plugging it into a personal computer, but the actual communication of this information to our rover was done via UART. As can be seen in this video, at any given time the rover's camera is only able to see one tile. As you can see, the motion of the rover is influenced by the resource or obstacle in front of it. As the rover continues to navigate the map, it will naturally come across many objects that the pixie can recognize. In addition to the information from the Pixie, the rover will also receive information from the server that specifies what the other rover on the team can see, and even what is expected to be on the visible tile based on the server's instance of the grid. There are various modes our project can be operated under, which specify which of the given data points, whether it be from the server or the Pixie, should be prioritized. Once this information is collected, the next step is the actual construction of the global game map. This is done by constantly updating the visible tile information and keeping track of where on the map the rover is based on how much it has moved. In addition, the map will store permanent objects on the grid, such as resources and obstacles, and apply a fog of war to other tiles on the map which may have changed since last being seen.
Next, to go into more detail about the pathing thread will be Keith.
The pathing for both types of rovers are done in a similar manner, with the only difference between the two rovers is the determination of the next tile, also known as the goal tile. The goal determination algorithm checks if one of the following questions is true, and determines the goal location based on the answers. Is the rover currently dead? Essentially, has the server determined the rover has been killed by another rover? This is also true if the game has ended, where effectively every rover has been killed. Does the rover need to return to the town center, possibly to return a resource, or to defend the town center from attack? Does the rover know where a resource is as a worker, or where an enemy is as a soldier? Are there any tiles that have never been seen, or is there any fog of war left on the map itself? In the case where none of these are true, the goal tile is selected to be the current location of the rover, until hopefully it determines a new goal to move towards. This default case should never occur, but is included as an extra buffer to determine the edge cases of this algorithm. As stated previously, this is the only component of the system that is different depending on if the algorithm is running on a worker or a soldier. After determining the goal tile, the rover has two algorithms for determining the next task, or the path required to reach the goal tile. These algorithms are what we call the turn right and the XY, YX algorithms. It is important to remember that only one of these algorithms is selected for use at a time, where which algorithm used is determined at compile time. The turn right algorithm is simplistic, where the next task taken by the rover is determined by the following question. Is there an obstacle in front of the rover? If so, the next task is to turn to the right. Else, the next task is to move forward. This means that while the rover would avoid obstacles and stay on the map, it would completely ignore the need to move towards the goal tile itself. This algorithm provided a simple means of testing and debugging the system and isn't used in what is the final implementation of the system itself. This is due to the fact that because it doesn't go towards the goal tile, it's never fully able to complete any single task as required by the rover. Unlike the turn right algorithm, the XY/YX algorithm took into account the goal location and tried to move the rover towards it in a simple manner. This was done by first determining the location of the goal tile relative to the tile the rover is currently on. After, the best path is chosen and consists of moving the rover horizontally, then vertically to reach the goal, or to move the rover vertically, then horizontally to do so. In this case, the best path would be the path that had the least number of obstacles. This was the algorithm that was used in the final implementation of the system itself. While both algorithms did work to some extent and allowed the rover to move around the field, they both had major issues, which include the lack of the ability to move around obstacles effectively, the lack of accounting for the inaccurate movements of the rover itself, and the need for both of them to use server data, which could have been outdated by the time either algorithm uses the data itself. Dealing with these many issues required additional work done in determining and working around the many edge cases that could be found when working with a pathfinding system.
The third thread created for our project was the rover state thread. This thread functions such that after receiving task information given to it by the pathing thread, the rover state thread sets the LEDs to represent the rover states as well as sets the motors to move as needed. Sensor data is also used for PID control and to determine the orientation and location of the robot on a tile. These commands are given to the appropriate physical devices. Specifically, more on the relationship between the rover state thread and the pathing thread is as such. The pathing thread sends a task message to the rover state thread. The rover state thread then decodes the task information and acts upon as such. For example, given the task of F, the rover state thread interprets the pathing thread as telling the rover to move forward one tile. The rover state thread then sets the motors appropriately to move the rover forward one tile. Other possible messages from the pathing thread include rotating right, rotating left, and moving backwards. Finally, Alex will walk us through the server and the IOCOM thread.
Hello, my name is Alexander Williams, and I will talk more about the implementation of our server in our game application. Our game's graphical application is implemented on a Raspberry Pi that communicates bidirectionally with the client rovers. The server's Python script handles incoming requests, which are either from the rover's UART via a Wi-Fi connection, or can be from a virtual simulated client. The rovers primarily provide location and rotation information to the server within a JSON payload. This information helps update the game state, and debug information in this payload is displayed in the server log. Before the game can be updated, this information needs to be placed in a MongoDB database. This is so our game application, which is another Python script, can easily access this information and then report back status changes and update the graphical display as stated in the project requirements. The status changes that are processed by the game application go back in the reverse direction through the MongoDB database and then accessed by the server script, and the server script then writes to the RX buffer of the Wi-Fi modules on the rovers or back to the virtual client so that the client can take appropriate action based on any given status changes. The graphical display in this case is the usage of the PyQt library in our GUI application. The PyQt library is the Python side of the Qt library, which is used commonly in graphical applications. Our server script utilizes a Python module called base HTTP server, which allows receiving and responding to HTTP requests on a certain port. One idea that could be implemented would be to combine the GUI application and the server script into one file. This would be good because of database accesses in MongoDB, which can be slowed depending on the number of clients trying to connect to the database. In the next section, I will give a short demonstration of our game on the actual application. So this is the graphical display for our game. Over here we have the configuration menu, where we can set unit locations, obstacles, and resource locations. After setting these configuration options, we can hit reset and simulate our game with a mix of either virtual clients and or actual rovers, depending on the options we selected. In this case, virtual clients are being started up in order to initialize the rovers. In this build of the game, I am also showing the view of the red units despite being on blue team in order to help demonstrate what's going on. Since many of the resources are placed near red, the red worker will get a resource first and bring it back to the town center, while the blue worker struggles to find any resources in order to activate its soldier. Some of the irregularities displayed, such as the red town center disappearing, are due to the debug mode of actually displaying the red unit's vision when this is likely not done in the final version of the game. In addition, the units sometimes looking around, yet not actually going onto space, are due to the random pathfinding algorithm that is occurring when the units are either in a gathering mode or a hunting mode, depending on their role. The end of this game actually results in red victory since the red soldier is able to find the blue town center and destroy it. In addition, the soldier also immediately defeats the blue soldier since it is at level 0, or in this case, not having been built yet because the blue worker never returned a resource.
At the end of it all, we definitely ran into some complications when trying to integrate, and we'd like to go over a few of those now.
There were a few problems when it came to integration with the rest of our project that I'm going to briefly touch on. The first was that our rover did not turn at exactly 90 degrees. Given that we calculated our current location based on how far it is turned, this led to the rover eventually navigating to the wrong tile, because our SLAM could only consider perfect turns. The second was that our game's physical implementation was different than its virtualization, meaning the server would occasionally suggest an incorrect move, report a different visible tile, or even misunderstand where the actual rover is located. The final problem we experienced was with the actual Pixie Cam, which operates optimally when it's taught objects with very bright hues. The magenta which we chose to use, unfortunately, was a little too dark to be picked up 100% of the time without error, so we had to change it out for a different color.
Thank you so much for watching this recap video of our ECE 4534 project. It was definitely a great time and we learned a lot from this experience. Please feel free to refer to any of our project documents if you have any further questions, or feel free to reach out to any of us. Thank you so much and have a great day.